Hello everyone, welcome to the video. Today we are going to solve the problem number of ways to make coin change. In this problem, we are given an array of integers. Every element of this array represents a denomination of a currency. For example, here in this coins array, we are given 1, 2 and 3. That means we have 1 rupee coins, we have 2 rupee coins and we have 3 rupee coins. We are also given that we have infinite supply for each of the denomination. That means we have infinite 1 rupee coins, infinite 2 rupee coins and infinite 3 rupee coins. Along with this coins array, we are also given a target sum. And we have to return the number of ways we can make this sum using the coins given in this array. So for example, here the answer is 4 because there are 4 ways of making the sum 4 using these coins, which are seen here. In the previous video, we solved this problem using the top-down dynamic programming approach. In this video, we will solve this problem using the bottom-up dynamic programming approach. Later, we will also see space optimizations of this bottom-up approach. We are going to solve this problem. We will go through the thinking process, we'll write the algorithm, and then we will also see a working code for that algorithm. So before we start, if you are new to this channel, please don't forget to subscribe and press the bell icon. Let's start. To begin with, let us first note down the key things given in the question. We are given an array of coins. Its size is n, and every element of this array represents different denominations of a currency. We are also given a sum that we have to make using these coins. We have to return the number of ways that we can use to make this sum using these coins. And we are also given that each of these coins we have in infinite supply. So if we consider an example, let's say we are given 1 rupee coins, 2 rupee coins and 3 rupee coins in infinite supply. And we have to make the sum 4. Then what will be the total number of ways? The total number of ways will be 4. Why? Because we can pick all 4 as 1 rupee coins. We can pick 2 1 rupee coins and 1 2 rupee coin. We can pick 2 2 rupee coins. We can pick 1 1 rupee coin and 1 3 rupee coins. Therefore, there are 4 ways of making the sum 4 using these coins. So if we consider our solution as a black box, we are getting as input a coins array as input, its size n, and a sum that we have to make. And we have to return the number of ways of making this sum using these coins. So what will our function signature look like? Our function signature will look something like this. Before we move to the bottom-up approach, let us briefly recap how did we solve this problem using top-down approach. So first of all, we made an observation that whatever are the ways through which we can make a sum using these coins, those ways either contain the last coin or they don't contain the last coin. Using this observation, we could make this statement that total number of ways that we are looking for is equal to number of ways that include at least one last coin and number of ways that don't include even one last coin. We formalized this statement into our recursive relation, where we could say that number of ways of forming sum equal to sum using first n coins is equal to what? It equals to number of ways of forming sum, which is equal to sum minus last coin value. That means we have picked at least one last coin. So number of ways of forming this sum using first n coins plus number of ways of forming sum equal to sum using first n minus 1 coins. So this corresponded to when we included at least one last coin, and this corresponded to when we did not include even one last coin. That means last coin was excluded. And we could also see that this include-exclude technique is very common. We then tried to write this recursive relation into our algorithm. So for that, we declared a method, a new method, number of ways util. This method would be called recursively. It took as input an integer n, which denoted that we will consider the first n coins from this coins array. Another input it took was sum, that whatever is the value of sum that we need to form. So using this recursive relation, first we calculated the answer for include by calling this same method recursively. Similarly, we calculated the answer for exclude case by calling the same method recursively for different inputs. Then we had our final answer and we could return that. But this itself was not complete. This would go into infinite recursion. So we needed to add base or terminating conditions. And what were our base or terminating conditions? They were that if sum reaches 0, then there is only one way of making 0 sum. That means, which is that don't pick any coin. So we returned 1. If sum was negative, then it is not possible to form this sum. So we return 0. And if n reaches 0, that means there are no coins to pick from. Therefore, there is no way of making sum. So we again return 0. Then this solution was complete, but its time complexity was very high because of overlapping problems. To solve the problem of overlapping problems, we used map, and therefore there was another parameter map to this function call. And what did we do with the map? Before returning the answer, we put the answer in the map against our input. And whenever we encountered the same input again, we first checked that in the map. If we could find it in the map, we did not calculate whole thing again. In fact, we returned the answer directly from the map. So this completed our top-down dynamic programming approach of the problem. As next step, we now need to think of the bottom-up approach. But why do we even need to think of bottom-up approach? What is the problem with top-down dynamic programming approach? The problem is recursion. In top-down approach, we use recursion. This method is calling itself again and again. And every method call occupies some space in the memory. So as the recursion tree grows larger, the space occupied in the memory will also grow large, which is not good. We don't want that. So it would be great if we could solve this problem in the same time and space complexity, but without using recursion. And therefore, we need to think of bottom-up approach. Let's start thinking about the bottom-up approach. Now, what do we mean by bottom-up approach? In the top-down dynamic programming approach, we started with larger input and gradually moved down to our smallest inputs, which were our base conditions. In the bottom-up approach, we move in the reverse direction. We start with the smallest inputs and then gradually move upwards towards the larger input. At the end, we will reach the solution to the input which is asked in the question. We will still use the insight of the recursive relation. We will still use answers of smaller problems to derive the answer for larger problem, but we are doing this in the reverse direction. Now, since we will still use this, that means we still have to store the answers to smaller problems. So we still need to store this information that for a combination of n and sum, this is our answer. And with storage of this information, we have one more requirement, that we should be able to easily iterate from smaller input to larger input, like from smaller combination of n comma sum to larger combination of n comma sum. So that means we can use a two-dimensional array here. So this can be our 2D matrix that basically holds the answers for combination of n comma sum. So what will any position in this matrix, let's say this one, denote? Any position denotes a combination of n and sum. And what does the value at any position denote? The value at any position will denote the answer for this combination. So if this position is I comma j, that means the value here will correspond to forming some j using first I coins. What are the total number of ways? Now n can range till n, which are the initial number of coins that were given to us. And similarly, sum can range from j equal to 0 till j equal to sum. We are iterating over the row by I and we will iterate over the columns by j. So now we have the dimensions of the matrix as well. Those are n plus 1 and sum plus 1. Now let's say if we had this matrix filled, do we have our final answer? Yes, our final answer will lie here. Why? Because this position corresponds to n and sum which are given to us in the question. So if we have this matrix filled, then we are done. Now, how do we fill this matrix? Let us try filling any general position in this matrix. Let us say we are trying to fill a position I, j, which is this. Now, as per this recursive relation, what all do we need to fill the answer for I, j? The first thing that we need is answer for I, j minus last coin value. Now, where will this lie? Clearly, this will lie in the same row as this one, but just a few columns behind. So let us say this position corresponds to this case. Now this case is the include case where we have included at least one last coin. Now coming to the second thing that we need is the answer for I minus 1 comma j. Now where will this lie? This will lie right above this. So the second thing that we need is in the previous row right above our I comma j. This means we should fill the matrix row wise, because then at any given point we will have all what we need. Okay, now we know how to fill our matrix, but from where should we start? We need to go to our base conditions to start. Now, what are our base conditions? Our base conditions are n equal to 0, sum equal to 0. We also have sum less than 0 as our base condition, but obviously we cannot represent a negative sum in this matrix because that would lie outside of the bounds of this matrix, negative indices. So we know that if any index is negative, if we are reaching at a place where index is negative, then our answer is already 0, because for sum less than 0 it is not possible to form that sum. So now let's try to take care of the base conditions, which are sum equal to 0 and n equal to 0. Now what does sum equal to 0 correspond to in this matrix? Sum equal to 0 corresponds to this first column. And similarly, n equals to 0 corresponds to the first row. So what will be the values for sum equal to 0? For sum equal to 0, we know there is always one way, that is, don't pick any coin. So we can fill all the values here with 1. Now what does n equal to 0 correspond to? N equal to 0 corresponds to this row. That means we don't have any coins, but we want to form some sum. Now it is obviously not possible, so we will fill this whole row with what? Zeros. We may think that for this point, as per this logic of filling the row, its value should be 0. And as per our logic of filling the column, its value should be 1. So what should we fill here? Actually, it won't matter, because this corresponds to 0, 0. And 0, 0 will be something that we will not encounter at all, even in our base conditions. So we can keep it anything. So now we know how to start filling the matrix. We know how to fill the value at any particular element. And we know that if this matrix is filled, what will be our final answer. That means we have everything to convert all of these our observations into algorithm. So let's try writing that. Clearly, we need to declare a matrix. Its size will be n plus 1 cross sum plus 1. We will initialize its first row with zeros and we'll initialize its first column with ones. Next, what we need to do is we need to fill this matrix row wise. That means we will iterate. In the first loop, we will iterate row by row. So our I will move from 1 till n. In the second loop, we will fill every row column wise. So we will iterate from j equal to 1 till j equal to sum. Now our aim is to fill the value at I comma j. That means we want to form j using first I coins, and we want to fill what are the total number of ways. Now to fill that, as per this recursive relation, we will first need what is last coin value. Now since we are dealing with only first I coins, what will be the value for last coin value? It will be coins I minus 1. Now, if we are talking about the include case, that means we have included at least one last coin. That means what is the remaining sum that we want to form? It is j minus this last coin value. But this can also be negative, and we know what is the answer for it being negative. The answer is 0. That is why we will add this condition. We will first check if j is less than this. That means j minus this will become less than 0. In that case, our include answer will be 0. But if it is not the case, then our include answer will simply be dpi j minus last coin value, something corresponding to 1 here. Now let's see how will we calculate the exclude answer. Exclude answer corresponds to the second condition of recursive relation. That means it will always be dp I minus 1 j. This corresponds to forming the sum j using only first I minus 1 coins. That means we have excluded the ith coin to form sum j. Now when we have include answer and exclude answer both, then we can fill the value of dpij as per this recursive relation, which will be equal to include answer plus exclude answer. In this manner, we can fill the whole matrix. And finally, as our answer, we will return dpn sum. Now what will be the time complexity of this algorithm? The time complexity will be big O of n into sum. Why? Because for every combination of n and sum, we have calculated the answer only once. And for that same reason as well, our space complexity will also be big O of n into sum, because we are using this matrix. Let us now go through the code for the same algorithm that we just discussed. You can also find the link to this code in the description. So this was our main function where we were given the coins array n and sum. N was the size of this array, and it also denoted the number of coins that we are using. So first of all, we declared a 2D matrix of size n plus 1 and sum plus 1. Then we filled its first row and first column. We filled the first row with values 0 and first column with values 1. Because first row corresponded to using no coins but forming some sum, which is not possible. And first column corresponded to forming sum equal to 0 using any coins, for which there is only one way. That is, don't pick any coin. Then we proceeded to filling this matrix row-wise. So we iterated. In the first loop, we iterated over every row from I equal to 1 till I equal to n. In the second loop, we iterated over every column. For every row, we iterated over every column. So our j ranged from 1 till sum. Now we had to fill the value at I comma j. That means answer for forming j using first I coins. For that, we needed what was the last coin's value. Now since we are using only first I coins, for us the last coin corresponds to coins array I minus 1. So the value of last coin value was coins of I minus 1. Then if we include at least one last coin, then our remaining sum that we need to form will be equal to j minus this value. But if this goes into negative, if last coin value is greater than j, then there is no way we can include last coin to form j. So that will lead to our include answer being 0. But if it is not the case, if our j is greater than whatever is the last coin's value, then what will be our include answer? Our include answer will simply be dpi j minus last coin value. What does that mean? Forming this sum, the remaining sum, using first I coins. Now the answer for the exclude case is even simpler, that it will always be equal to dpi minus 1 j. That means forming sum j using only first I minus 1 coins. So dpij will be equal to sum of these two. So this way we will fill the whole matrix. And finally we will return dpn sum as our answer. So this completes the code for bottom-up dynamic programming approach for the problem number of ways to make coin change. The time and space complexity of our previous solution was big O of n into sum. An extension to the problem can be if it is possible to solve this problem in a lesser space. Let's see if we can reduce the space complexity, if it is even possible. Our space complexity was big O of n into sum because we were using this matrix. Now let us see that do we need this whole matrix at any point in time in our algorithm. Let us see how we are filling the value at point I, j. To fill the value at I, j, we need first answer for I, j minus last coin value. And where will this lie? This will lie on the same row, just a few columns prior to it. We also need the second thing as answer of I minus 1, j. Where will this lie? This will lie just in the previous row, right above it. That means at any point in time, whenever we are filling the value at any particular position, we at max need two rows only. One is the current row and one is the previous row. Even if we had filled 1,000 rows prior to this, we won't need them. If we have the previous row, we can fill the current row one by one, column by column. So if we could solve this problem using only two rows instead of the whole matrix, our space complexity will greatly come down. It will come down to big O of sum only. So let's see how can we do that. So let's say these are the two rows that we declare, previous and current. Now what will be the sizes of these arrays? The sizes will be same as number of columns in this matrix, which will be equal to sum plus 1. Now, what do these two rows represent? The current row represents the answers for sum equal to 0 till sum equal to sum if we are using only the first I coins. Now let's see what does every position in this row correspond to. Every position would correspond to a sum equal to j using first I coins, and the value at every position will correspond to the number of ways of making sum equal to j using first I coins. So let us see how will we fill any position, let's say j, in this array. To fill value at any position j here, we need two things. The first thing is the value at j minus last coin val using the first I coins. So where will that lie? That will lie in the same current row, let's say somewhere here. The second thing that we need is forming j using first I minus 1 coins. So where will that lie? That second thing will lie in the previous row, right above it. So now we know that we can fill any value at any position j for the current row using the answers from previous row and the previous answers in the current row itself. Great. That means now we know how to fill the value at any position. But how will we get our final answer? We will get our final answer when I corresponds to n, the total coins that we are given, and j corresponds to the sum. That means when I corresponds to n, this last element will be our final answer. So now we know how to fill any value in the current row using previous row. We also know how will we get our final answer. But we yet don't know how will we start. How will there be values in the first previous row? Now the first previous row will correspond to the first row here, which is our n equal to 0. That means there are no coins to pick from. And in that case, we know our answer is always 0 because this is our base condition. For current row, we know that always its first element will have value 1 because the first element corresponds to sum equal to 0. Great. Now we know how do we start with previous and current. We know how to fill any value at particular position in current row. Now we need to think of what will happen when we move from one iteration to another. Let us say we are currently filling the values for I equal to 2. Now when we move from I equal to 2 to I equal to 3, what happens? In that case, this current previous will not be useful for us at all. It will be a complete waste. But this array, answers for I equal to 2, will serve as previous for I equal to 3. Therefore, our previous will point to current before moving to next iteration. Therefore, as we move to next iteration, our previous will point to current, and the values that were previously there in this array will be of no use to us. So now we know that we have to have these two arrays. How do we start filling these two arrays? We know how to fill value at any particular position. We know how to move forward iteration by iteration, and we know where will our final answer lie. That means we have everything to formalize this into algorithm. For the algorithm, we clearly need a new array previous whose size is sum plus 1. And we also need to initialize it to all zeros because we will start from the first row. This first row will correspond to previous here. And then we will start filling the current, which is from I equal to 1. And that means we have to iterate from I equal to 1 till I equal to n and fill every time fill a new current row. So we iterate from I equal to 1 till n, and in every iteration our aim is to fill a new row, current row corresponding to this I. So we will have a new current row with size sum plus 1, and we know what will be its first element's value. Its first element's value will be 1 because it corresponds to sum equal to 0. Now we have to fill this current array from left to right. So we have to again iterate. In every iteration, we have to fill the value of current at index j. Now to fill that, we need last coin value, just like in the previous algorithm. So we get the last coin value. Then we also need to handle the same condition that we handled here, that sum should not become negative. If sum becomes negative, then our include answer is 0. Similarly, if it is not the case, then what will be our include answer? It will lie in the current row itself. It will lie in the current row, but just a few columns prior to it, as we saw in the previous slide. And exclude answer will lie in the previous row for the same column. This also we saw in the previous slide. So what will be the value at current j? It will be equal to include answer plus exclude answer. Now, as we complete the iteration, as we completely fill our current row, now we have to fill a new current row as we will come here. But for the new current row, what will be the previous? The previous will be this current row that was filled in this iteration. And what happens to the previous that was here in this iteration? That is of no use to us. So we will set our previous to current, and then we will return once we are done with all the iterations for all the rows. Then we will return previous of sum or current of sum. Both of them will have the same value. So this completes our algorithm of space optimized bottom-up dynamic programming approach. Now what will be the time complexity and space complexity of this approach? The time complexity will still be big O of n into sum because of two nested loops. But the space complexity will now be only big O of sum because we are only using two arrays whose sizes depend on sum. Now one may think that here in every iteration we are initializing a new current array. So does that not mean that our space complexity should be big O of n into sum? Where are we going wrong here? To find that, let us see what happens in the memory when we declare our previous and current arrays. So the first time we declare this previous array, a memory of size this will be allocated and a pointer previous will point to it. Something like this. Similarly, when in the first iteration we create a new array current, again the similar thing will happen. A new memory is allocated and a pointer current is pointing to that memory. Now we fill this current value, the values in the current row one by one. That happens. Okay. Now what happens before we move to the next iteration? Before we move to the next iteration, we point our previous to what our current is pointing to. That means at this time our current and previous both point to this memory location, and previous is now not pointing to the previous memory location. Now this memory location, no pointer in our program is pointing. So this memory location has now become inaccessible for our program. Therefore, whatever is the garbage collection mechanism, that will free up this space in the memory. And at this point, there is only one row occupied in the memory. So when we come to the next iteration, we declare another row and point our current here. So again, a new memory is allocated and our current points to that position, that memory. Our previous is still pointing to the previous current memory location, and the connection between current and the previous memory location is now broken. Therefore, now again there are only two rows here. Now this will go on in every iteration, and every time at any point in time we will have only max two rows occupied, and that is why the space complexity is big O of sum only. Let us now go through the code for the same algorithm that we just discussed. You can also find the link to this code in the description. So first of all, we initialize an array previous of size sum plus 1. We initialize it with values 0 because this first corresponds to the case when there are no coins to pick from and we have to make a sum. So when there are no coins, then the number of ways of making the sum equals 0. Then we iterate. We iterate from I is equal to 1 till I is equal to n. I corresponds to the first I coins that we can use. So in every iteration, we will fill an array current. So we declare a new array current in every iteration of this size. Now this will correspond to some answers for sums from 0 till sum when using the first I coins only. So the first element of current is initialized with value 1 because this corresponds to sum equal to 0, and for sum equal to 0 there is only one way, that don't pick any coin. Now we fill the array current from left to right. So we iterate from j is equal to 1 till j equal to sum. Now to fill the value at any position j, we first need the last coin value. Now last coin value will be coins I minus 1 because we are using only first I coins. Now our first aim is to get the include answer. What is the answer if we include at least one last coin? Now if we include at least one last coin and remaining sum becomes negative, then therefore in that case include answer will be 0. But if the remaining sum does not become negative, then our answer will lie in the current row itself, just a few columns prior. Now our second aim is to find the answer for exclude case, when we don't include the last coin at all. That means we have to form the sum j using first I minus 1 coins only. So we can find that here in the previous row, previous j, and that way we can fill the value at current j. So by filling this, by going through all the iterations, we will have the current row filled out. So in the next iteration, we will move to the next current row. Now, but this current row will serve as previous for the next iteration. Therefore, we point our previous to current, and this previous that we had begun with in this iteration will be of no use to us. So when we are done with all iterations including I equal to n, our answer will lie in either previous of sum or current of sum. So this is the code of the space optimized bottom up solution for number of ways to make a coin change. Let us now see this code in action. So we will provide it input and let's see what output it throws up. So we are providing one test case. In the one test case, the sum that we are providing that we have to form is equal to 4. And we are giving 3 denominations. Those 3 denominations are 1, 2 and 3. So let's see what is the answer. The answer is 4. This is it for this video. If this video was useful to you in any manner, please let us know by commenting below. Also let us know in the comments what will be the next problems that you would want to see on this channel. Please don't forget to like and share the video and subscribe the channel. We will meet again in the next video with some other problem. Thanks for watching.